Okay, welcome back to the presentation on AI or computer science beyond Buzzword Bingo. I'm Martin Kool. Next to me is my son Joep,
Hi.
who will be helping me through this presentation. So, back to the question, how do you train a computer? Train a computer? Well, consider that you get a new colleague. So the new colleague enters in the morning. What do? Well, obviously, you have hired this person, then you onboard him. The person gets a computer, a desk, a telephone, business cards, for instance.
American Psycho like.
Yeah. You train the person, then in general, the person gets tested whether the knowledge was applied, and this can be more rigorous than others. Obviously, if you're want to be a chartered accountant, then the test is a little more than if you work in a call center. And finally, you actually get to apply your knowledge. And if any of these steps go wrong, you actually take a step back. And ultimately, if you really mess up, then you actually restart hiring and you get laid off during your probation period. Now, suppose this is not a person but a computer. What do you think will be different? Well, not a lot actually. So you get the data, you select the model, you train the model, you test the model, and then you apply the model. Very similar steps, and you take a step back if needed. You can take this even a step further. For instance, if you're focusing on training, you ask yourself the question, what needs to be trained? How will it be trained? You transfer the knowledge and you see if it worked. Yeah, so you set goals, you prepare material, you learn the material, and you assess the material. And if somebody flunks the exam, then you take a step back. So far, so good. Now, a computer actually, or a computer model, is actually the same. You set a learning target, typically called the Y. You prepare the features, which is typically called X. You run the model, you validate, and if something goes wrong in the cross-validation or you don't like the model, you actually rerun it. Now, what can you take an example? How would this work? Well, actually, you can ask yourself, the computer, is this a cat? Now, this is all manually prepared, but it actually works this way. So you feed the computer with a bunch of pictures, which are labeled whether they should be considered a cat or not. Yeah, and then you test a set of pictures whether the algorithm identifies the cats properly. Well, obviously, in the first instance over here, this is not a cat and was clearly identified as such. Here is a mouse, which was also not considered to be a cat. These two are cats and were identified as such, and obviously this is not a cat either and wasn't identified. Actually, only the dog that was labeled as a cat, and you can well imagine it is the way
similar
it looks.
Features.
Very similar features.
Same coloration, also pointed ears.
Absolutely. So this could well actually be in practice, and this is actually how it works. Now, this is an example of supervised learning. You can also do unsupervised learning. You can also feed all the pictures to the computer and ask, okay, make categories. Now, so then they start labeling. For instance, label 1 would mean 2 ears. This is done manually, so I know what I did. Number 2 was 3 or 4 legs. Number 3 was a single eye. And number 4 was an open beak. Now, always in all the presentations, somebody will ask, well, will you do it? Why?
Yeah, why is the crocodile labeled 3? Or is it an alligator? I don't know.
Yeah. Whether the crocodile or alligator had this enormous open mouth, well, then obviously the algorithm determines that the single eye is more important than this enormous open beak.
Yeah, you can say the same about the lion.
Absolutely. So that's how it actually works. A good example, this is a famous picture of the so-called Olivetti faces. And this is actually a data set from the early 70s on which facial recognition was initially developed. It's the actual original data set. That's what it looks like. Now, this leads also to a slight side alley on, facial recognition. How does that actually work? Because of all kind of difficulty with the GDPR, the General Directive on Data Protection, I took the picture of myself and my lovely wife, and you can see how it works. So you center the original, you crop and rotate. It happens everywhere, and then it starts recognizing features, and both these features are actually transferred to a single roster, how do you call that, set of axes, and you can actually see how people are distinct. And that's how you can also see that the differences, how that is done. But it also begs the other question, or the other question around, why do I sometimes, when I go for a passport picture, have to deal with so many rules around the way I should be looking into the lens? Well, that has to do with the desire to make an unsupervised problem into a supervised problem. So if we saw with the cats, the cats, if you tell them to recognize cats, it can, but if you tell it to recognize anything, it won't actually identify cats. And that is typical for unsupervised problems. So the more you can turn an unsupervised problem into a supervised problem, the better, because supervised generally actually works a lot better. But it begs the question of, how do we actually learn? Now, this is not a trick question. What is this?
A bird.
Well, correct. What is this?
A fish.
Well, correct. But how do we know it is a bird? Well, we know it because it's got wings, it's got 2 legs, a beak, and it flies. And it is a fish because it's got gills, it's got a tail, it's got a fin, and it swims. Yeah? What we actually do is something called pattern recognition. So, if we do pattern recognition, what is this? It's got a tail, it's got fin, gill, and it swims. So it must be a fish. Now the question is, what is this? Actually, is this a fish? Well, it doesn't swim, but it does have gills, it does have a fin, and it does have a tail. So, what is it? What we actually do is called KNN, K next neighbor. So you look at the closest K number of neighbors and take the closest. So for instance, this was a fish because although it doesn't swim, it does have a gill, a fin, and a tail. It isn't a bird. Although it flies, or appears to fly, it doesn't have a beak, it doesn't have legs, and it doesn't have wings. But it's not a dog either, because it doesn't walk, it doesn't have a snout, it doesn't have 4 legs, but it does have a tail. Now, somebody very clever in the audience, or even my son earlier this afternoon, actually mentioned that this is actually not a fish. Well, no, it isn't. However, it all depends on what the neighbors are. So if you don't feed the information that this is in actual fact a mammal, it will actually always find the closest.
Yeah, so mammalian marine animals need to be qualified in of themselves to actually be identified properly.
Yeah. Now, something else, a way to learn is decision trees. For instance, how do we commute to work? By a bike or a car? Well, for many people this is an easy question, but you can also do it more lightly, more scientifically. So ask yourself the question, does it rain? Well, if it doesn't, the question is it cold? And if it isn't, then you take the bike. And if it is cold, you take the car. If it does rain, you can ask yourself, is there heavy traffic? And if there isn't, you take the car. And if there is, you take the bike. So you actually build up a decision tree. And based on this information, you can actually predict. So if it doesn't rain, it's 19 degrees Celsius and the traffic is light, you can actually determine what the likelihood is that somebody takes a bike or a car. Now, that comes in handy if you do a traffic service and you need to predict the number of traffic jams in the morning. So that's how that actually works. Now, I'm a numbers fetishist. So what I do, I play tennis, and for a month I actually recorded whether I went to play tennis, whether I had my racket with me, whether my partner was available, whether there was a lot of wind, whether there was temperature, and what the weather outlook was, and whether the courts were wet or not. And actually, if you feed this, then the computer or the algorithm actually determines a decision tree very, very easily. And the interesting thing is that the humidity of the courts is not actually a consideration at all. It doesn't actually matter. Now, why is this useful? Well, it's useful for my wife because she only needs to know whether I had my racket, my partner, there was wind, temperature, and outlook, to know whether the state of drunkenness I would get home in the evening. So this is how you actually can learn. You look at the pattern. Now, decision trees actually get complex very fast. So instead of one big tree, what we typically do nowadays is actually create a lot of small trees, which is called a random forest. And we'll get to that in a later stage. Also, something similar happens with deep learning versus in neural networks. Up to now, I've shown you what supervised learning does. And in the next clip, we'll continue on unsupervised learning.